Okay, so now we're going to try to do some error analysis of collocation methods. So let's start by seeing whether there's a way to connect, if you will, the error analysis of collocation methods with the error analysis of numerical quadrature rules. Okay, so imagine you have a candidate solution. So let's say we're given a candidate solution, or a sort of approximation, if you will, of the solution. Let's say V. Okay, then you can basically compute what is called the defect, which more or less measures the extent to which V satisfies the defining differential equation. Okay, so let's consider, we define the defect. Okay, so this is d of t, and this is just defined to be v prime minus f v of t comma t. Okay, so this is the extent again to which v satisfies the defining differential equation. And so clearly there has to be a relationship between the magnitude of the defect and the error. Okay, so there should be a relationship sort of between the defect and the error. Okay, which is defined to be v of t minus y of t, where of course y of t is the solution of the differential equation. Okay. And in particular, of course, if we had chosen V to be the exact solution, and then the defect would be identically 0. And so again, we want to be able to say to some extent that if you have a small defect, then there is somehow a small error as well. Okay. So we expect that a small defect say the norm of d of t, right, implies that the error is small. Okay, so let's try to make more precise. It's like, and more rigorous. It's like that kind of intuition. So let's start with a simple case, in particular the case of a linear differential equation. So let's consider a linear equation. Okay, so that would be, for example, y prime is lambda of y. Okay, and then y at t0 is equal to y0. Okay, so you have some initial value problem like this. And then, of course, you define the defect. D of t is equal to v prime of t minus lambda v of t. Okay, and so so you can rewrite this to get a linear unhomogeneous equation, right? So we can rewrite this to obtain a linear inhomogeneous equation. Right, which says that v prime of t, right, is equal to lambda v of t plus d of t. Okay, so if you didn't have the defect, then of course you just have a linear differential equation, but now you have the d of t term, it's like, which is an inhomogeneous term. Okay, all right. So so then you can write down the exact solution of v. It's like using the variation of parameters formula, or variation of constants formula. Okay, so the solution of v of t can be obtained using the variation of constants formula. Okay, so it says that v of t is equal to e t minus t0, right, lambda acting on v0 plus the integral from t0 to t of e to the t minus tau, lambda acting on the defect d of tau d tau. Okay. And of course, it's like you know what the solution of this differential equation is. So let's just erase this first for now. Okay, so let's write down the exact solution. We know that y of t is equal to e to the t minus t0 times lambda acting on y0. So the error, right, which is v of t minus y of t, is just going to be equal to e to the t minus t0, lambda acting on v0 minus y0, plus the integral from 0 to t of e to the t minus tau, lambda d tau d tau. Okay, so so you know you can compute what the initial error is, all right, and then there's a defect term which you can measure in some sense. Okay, so the upshot, if you will, is that the error can be expressed in terms of measurable things, quantities or observable quantities, like the difference between v0 minus y0 and the defect. Okay. D of t. All right, and perhaps that's not so surprising that you can do this because in the case of a linear differential equation, you happen to know what the exact solution is, and then that allows you to leverage this variation of constants formula. It's like when applied to the inhomogeneous equation, it's like which relates the sort of candidate solution y and this defect quantity. All right, so that's perhaps not so surprising. Then the question is whether or not, to what extent you can generalize, it's like this kind of reasoning, to the case of a nonlinear differential equation. Okay, so so let's see what happens in the nonlinear setting. So question. And basically, it's what the question is there something like the variation of constants formula in the nonlinear setting? Okay. for a nonlinear differential equation. Okay, and there's a sense in which there's a slightly weaker form of this, which is called the Alexeev-Grobner lemma. Okay, so there's a theorem. Okay, so this is theorem 3.6. Alexeev-Grobner lemma, and the following is the statement that, let's say you have V be a smoothly differentiable curve. Okay. Well, smoothly differentiable function. Okay. That sort of obeys the initial condition that V at time t0 is y0, then this error, okay, V of t minus y of t satisfies this kind of relationship. Okay, that so if, of course, if v at t0 is y0, then this term at the top vanishes, and you're just left with this integral term. So we're hoping to get something like that integral term, which relates again the defect and some sort of operator integrated over the domain, the time domain, to the error. Okay, so something similar happens. It's like in this Alexeev-Grobner lemma, that if you integrate from t0 to t of some function phi, okay, of t minus tau, and then some v of t minus tau applied to d tau, then that turns out to be the error which you get, where this map here is a matrix involving partial derivatives. Right, of the solution of the ODE. W prime is equal to f of wt, right, where w of tau is equal to v of tau. And then you do this with, and you take derivatives of this with respect to v of tau. Okay, so the problem, of course, is that this matrix is in general unknown, but it is actually possible to estimate it nevertheless efficiently, which turns out to be useful when you're trying to do error control. But for the purposes of the error analysis, which we're going to perform for the collocation methods, you don't actually need to compute that explicitly. Okay, so let's state the following theorem. And maybe let me just write that down. Okay, so v of t minus y of t is equal to the integral from t0 to t of this matrix t minus tau, v of t minus tau. All right, the defect evaluated at tau, d tau. Okay, all right. So let me now state a theorem. It's like about the order of accuracy of a collocation recursive method based on certain properties of the collocation points. And you'll see that those properties of the collocation points are related to the kind of properties you have seen in the order of accuracy of Gauss quadrature rules, and it involves certain orthogonal polynomial properties. Okay, so let me state the theorem. So theorem 3.7 states the following: that suppose that this integral from 0 to 1 of q tau, tau to the j d tau equals to 0. And of course, this is nothing more than the inner product between q and tau to the j, all right, for a suitable choice of inner product. Okay, and more or less says that q and tau j are orthogonal. Okay, so we saw this before when we were looking at the error analysis of, for example, Gauss quadrature methods. And this happens for j equals to 0 all the way up to n minus 1. Okay, for some m, which is in the set from 0 all the way up to s. Okay, where this polynomial q of t is just a product from L equals 1 to S of T minus CL. So it's basically a polynomial. It's like which involves multiplying sort of linear terms. It's like which have roots at the collocation points. Okay. And again, we saw something like this when we were looking at the error analysis of Gauss quadrature rules. Okay. So if you have that, then the claim is that the collocation method both it's like in its sort of original form as well as its corresponding Runge-Kutta method, okay, is of order S plus M, if you will. Okay, so that's the theorem. It's like, and as it turns out, when we do the error analysis, it's going to be related to this Alexeyev-Grobner result, which I've written down here. Okay, so let's prove this. Okay, so we want to express the error of the collocation method using the Alexeyev-Grobner formula. Okay. All right, so what you're saying is that yn plus 1 minus, let's see, y tn plus 1, so I'm looking at the difference between the numerical solution coming from the collocation method and the error coming from, oh, actually this is the exact solution, so it's the error between the numerical method and the exact solution, right, is equal to the integral from Tn to Tn plus 1 of this matrix, this unknown matrix, evaluated Tn plus 1 minus tau, u of Tn plus 1 minus tau. Okay. Where u is the if you recall, is the element of the polynomial space which is used to define the collocation method. Okay, and then there's the defect d tau d tau. Okay, so the art, if you will, it's like in using this Alexeyev-Grobner formula comes from the fact that, if you recall, the collocation methods, at least when you think of it as finding a distinguished element of some polynomial space, comes from the fact that that distinguished element of the polynomial space agrees with the initial condition, as well as satisfying the differential equation at the collocation points. All right. So the idea, if you will, is that the defects d at the collocation points vanish. Okay, and so if you were somehow smart, and then what you want to do then is you want to approximate this integral, right, by a quadrature rule which has basically as its quadrature points the collocation points. And so what would happen then is that the quadrature approximation of this integral is just going to be 0 because the defect at those times, at those points will be 0, and then it doesn't matter that you don't know what this phi matrix is, okay, because it's like it's being multiplied into something which vanishes. And so more or less it's like what happens then is that this allows you to say that the error in the collocation method is basically just given by the quadrature error you make by replacing this integral by some sort of quadrature rule where the quadrature points are the collocation points. Okay, so the remark is that at the collocation points, right, d of basically Tn plus Cih vanish. And this is just by definition of the collocation method. Okay, and so if we approximate the integral by a quadrature rule, right, with quadrature points given by the collocation points, then the quadrature approximation of the integral is 0. Okay, and so basically what happens then is that that integral, of course, is the quadrature approximation plus the quadrature error, and so you know, the global, well, the local error, it's like of the collocation method, is then related to some quadrature error. So the integral, right, is just sort of bounded, if you will, by the quadrature error. Okay, and so the nice thing again is that what that allows you to do in this framework is to relate the error properties of the collocation method with the error properties of the corresponding quadrature rule, where the quadrature points of that quadrature rule are the collocation points. Okay, so let's see what happens when you do that. Okay, so let me just sort of state this. So I said this in words, it's like, but let me sort of just write it down sort of more precisely. So this is telling you that yn plus 1, right, minus y at Tn plus 1 is equal to this quadrature approximation, j equals 1 to s of bj. All right, this sort of a known matrix, which I don't really want to compute. All right, and u at Tn plus Cjh. So again, as a reminder, u is the polynomial which satisfies the collocation condition that when you take this polynomial, you differentiate it, and you substitute it into the differential equation, then it actually does satisfy the differential equation at these collocation points, right? So, all right, and then the Tn plus Cjh, right? So this is a quadrature approximation of the integral, and then there's the error plus the error of the quadrature. Okay, so this is basically what I said in words down here. Okay, but by definition of the collocation method, right? D at Tn plus Cjh is equal to U prime Tn plus Cjh minus F U Tn plus Cjh Tn plus Cjh. All right, and then again, by definition, it's like this U satisfies the differential equation at the collocation points. So this is 0, and so what that means is that this quadrature approximation of the integral vanishes, and then you're just left with the error of the quadrature. Okay. So, so by sort of the result, it's like which relates the quadrature error with the sort of orthogonality properties of the sort of polynomial Q of t is the product over j equals 1 to s of t minus Cj, right? We conclude that the error, quadrature error, is big O of h to the s plus m plus 1. So the order of the collocation method is s plus m, right? Which is what we were trying to prove. Okay, so this is a really, really nice way of proving things. It uses this Alexev-Grobner formula, and of course, again, there's this unknown matrix. It's like which is in principle difficult to compute because it really requires you to be able to solve the differential equation. But because it's like you have this collocation method for which the defect vanishes at a bunch of points, you can then use it's like those points. It's like as the quadrature points to approximate this integral. All right, and so what happens is that then the quadrature approximation of that integral vanishes, and you're left with an expression which relates the local error, if you will, it's like of your method with the quadrature error of that method. And because of what we proved about relating quadrature error with the orthogonality properties of this polynomial, which is obtained by taking linear factors which have roots at these collocation or these quadrature points, then you end up with this result, which says that all you have to do is like to check the order of a collocation rule or collocation method is to look at the collocation points, all right, and then you construct this polynomial Q of t. You just compute it's like these inner products between Q of t and t to the k, right? Starting with k equals 0, and the more of these it's monomials it's like this Q of t is orthogonal to, right? Then the higher the order of the method, then sort of the minimal order, which is s. All right, so that's a really nice result here. It gives you a very, very systematic way to do error analysis of at least a class of Runge-Kutta methods. And as we saw, it's like if you were to try to do the error analysis of a Runge-Kutta method by hand using Taylor expansions, that's extremely time-consuming. And it's quite a sort of involved exercise. So we'll talk a little bit about how you can more systematically do the error analysis of Runge-Kutta methods using the concept of what are called rooted trees, which give you a nice combinatorial way of tracking, if you will, the derivatives you get. It's like when you take the total derivative and you write it in terms of f times d dy, for example. And so we'll study that it's like in a little bit.